Hello friends, welcome to this lecture on Bode plots. In the last class, we discussed a few things about Bode plot. Just to recapitulate, while analyzing any of the physical systems by using mathematical modeling, the next step is to carry out its time domain analysis and frequency domain analysis. And particularly in frequency domain analysis, we carry out frequency response analysis. And in that frequency response analysis, we focus on Bode plot, logarithmic plot, polar plots, Nyquist plots. Like this, we provide the input frequency functions and we solve those equations of operations and transfer functions for those frequency inputs, and the solutions are plotted on various plots or various diagrams, and from these plots or diagrams we analyze the system behavior and we predict the system behavior based on those graphs. And this analysis helps in predicting the system behavior while working on paper. That is one part we discussed in the last class. Secondly, as a designer, we can suggest improvements in the system performance by modifying the system parameters. And these parameters help the designers in providing the range of values of various parameters within which limits, like we took the case of a spring mass dashboard system or a suspension system. What should be the limiting value of the masses those we are going to use? What should be the limiting values of the stiffnesses we are going to use? What are the limiting values of the damping factors we are going to use? So that the system performance is optimal or the system remains stable within the performance limits. So this is what we discussed in the last class. And we also discussed about the importance of pole zero plots in control system analysis. We understood in the last class that the numerators of the transfer functions provide us information about the zeros of the system, and the denominator factors help us in providing the poles of a given transfer function. And when we have that pole zero plot in the S-plane, where x-axis is the real axis and y-axis is the imaginary axis. When we plot these poles and zeros on those plots, we also concluded in the last class that if in general, if the poles and zeros lie on the left half of S-plane, the system is stable, and if the poles and zeros lie on the right half of S-plane or right half of imaginary axis, the system is unstable. And if the roots lie on the imaginary axis, the system is conditionally stable or marginally stable. Now, having understood all those aspects, remember, we have not built a prototype yet. We are still working on a mathematical model of the system. And using these pole zero plots also, in general, I can suggest to the designer that, I suggest to the operators that design these systems within these values of steady state gain so that the system remains stable in its performance. If you cross the limiting value of K, steady state gain value K, beyond this value, the system will tend to become unstable. So this is what is the benefit of all these frequency response plots and pole zero plots. We can get to know about the system performance characteristics and we can improve upon the system behavior. If you go ahead, we can design some of the compensation circuits even, so that lead lag compensation circuits can be incorporated in my control system, and whatever are the predicted performance characteristics, those can be improved by using these compensation techniques. So this is what we discussed in the last class, friends. Continuing with that discussion, in the last class we also talked about Bode plot. Bode plot includes two graphs. One graph was magnitude plot and magnitude versus frequency plot, and the second plot was phase angle versus uh, rotational frequency or angular frequency plot, or magnitude versus log of omega, and second plot was phase angle phi versus log of omega. So this is what we discussed. Now we'll see, given a transfer function, how to plot these Bode plots, Bode magnitude plot and Bode phase angle plots for various factors those are involved in the transfer function. Now, what are the various factors? As we know, friends, the transfer function of a given system, how to find out the transfer function, that procedure we already know. We write the equation of operation, and then we identify what are the input parameters and what are the output parameters, and we take a ratio of output by input as the transfer function. And on the right hand side of this output by input function, will be getting a transfer function in either time domain or in uh, S domain, Laplacian domain. So we already know the procedure for finding out a transfer function, either by using mathematical models directly or by using block diagram techniques. Also, we can find out the transfer function of a given system. Now, in that transfer function, there'll be some numerator, there'll be one denominator, isn't it? That output by input ratio, which is the transfer function, will be equal to some terms in the numerator and some terms in the denominator. In the numerator, I might have a constant term k, some number which corresponds to steady state gain. So I'll have a constant term k. Now we are going to see how to have a plot, Bode magnitude and Bode phase angle plot for this constant term. I can also have poles at the origin. What do you mean by poles and zeros? We already identified. The denominator values of the factors correspond to poles of the transfer function, and numerator values of that transfer function correspond to zeros of that transfer function. And we also remember that those are called as zeros because by putting the values of those parameters, the entire transfer function becomes zero, as they are called as zeros of that transfer function or zeros of that system. And regarding poles, those are the denominator values. By putting those factorial values or factor values in the denominator, the ratio becomes infinity, and that's why they are called as poles of that transfer function, or those are also called as poles of that system, right? So if I got poles at the origin, if I got S term in the denominator, what do you mean? If you remember the last example we had taken, S term in the denominator. If I put S is equal to 0, the denominator becomes 0. So numerator upon 0 makes it infinite. Hence it is called as the pole of that function. Now, what S is equal to 0 means? So that pole is at origin. S is equal to 0 corresponds to origin of that S-plane plot, if you remember, isn't it? So poles at origin, I can either have S terms or squares or exponents of S terms. I might have S, that is a single pole at 0. If I got S square, there will be double pole at 0. If it is S cube, there will be triple pole at 0, or S raised to n. So n number of poles will be available at origin, right? So that power corresponds to, power of S corresponds to the order of the poles. If I got S is equal, only single S to the power 1, so I got single pole at the origin. This is what is meant. So we'll learn how to have a Bode plot, both magnitude and phase angle plot for poles at origin. Similarly, Bode plot for zeros at the origin, right? When I have got S term in the numerator or S to the power n term in the numerator. So I'll have single zero at origin. I will have double zero if I got S square term. If I got S to the power n term, I'll be having n zeros at origin, right? Then I'll be having a factor called as simple pole or the first order factors in the denominator, like S plus 1. I'm writing it specifically in 1 plus S form. The relevance will be understood when we go in for plotting. It is either S plus 1, S plus 2, S plus 3, whatever it is, S plus 100. term at the denominator. That is called as the first order pole, or it is also called as simple pole, right? And whatever is the factorial value, s is equal to -1 makes the denominator 0 and the ratio becomes infinity. So s is equal to -1 is a simple pole at 1, at -1, isn't it? So in frequency domain analysis, what we do? We put s is equal to j omega. So the ratio becomes 1 upon 1 plus j omega in place of 1 upon 1 plus s. S is equal to j omega makes it 1 upon 1 plus j omega. Mod of that gives me magnitude of that simple pole. Similarly, I might have a factor in the numerator which is called a simple 0. So it's a first order 0. This is if I have a factor like s plus 1, s plus 2, s plus 50, s plus 25, s plus 1000, whatever it is. So that is called as simple 0 or first order 0. So when I substitute s is equal to j omega in the frequency domain analysis, it becomes mod of 1 plus j omega. And mod gives me magnitude of that simple 0. And I might have complex terms in the numerator, complex terms in the denominator. So in a sense, the factors are complex numbers. So, and I might have higher order poles and zeros also. So if I have a term like s plus 1 bracket raised to 2 is a second order 0 if it is in the numerator. If it is in the denominator, it is called as second order pole. If I have a cubic term, it will be third order poles and zeros. Likewise, I may have a quadratic factor even. So we are not interested as far as our curriculum is concerned. We are not going into details of higher order poles and complex poles. We'll understand the Bode plotting procedure for constant term, poles at origin, zeros at origin, simple pole and simple zeros. We'll see one by one what are the methodologies of plotting these Bode plots. First, constant term k. Let us see the magnitude plot. Constant terms such as k. Now, k might correspond to some number. When we take an example, we will understand that. In the transfer function, some constant number is there. I might have 50. I might have maybe 1000. So that corresponds to constant k, which is called as the steady state gain of that system. The constant terms such as k contribute a straight horizontal line of magnitude 20 log to the base 10 of k. So what I need to do to have a plot on the semi-log paper, if you remember last class, semi-log paper, x-axis is the logarithmic scale and y-axis is decimal scale. Hence it is called as semi-log paper. So on the x-axis, I will start with maybe 0.1. So I'll be having divisions of 10 logarithmic scale divisions. So 0.1, 1. So this is called as 1 decade, isn't it? 0.1 to 1, 10 steps, 1 decade. 1 to 10, 1 more decade. 10 to 100, steps of 10, steps of 1, steps of 0.1, right? 0.1, 0.2, 0.3, 0.4, 0.9, and 1. 1, 2, 3, 4, 5, up to 10. Then 20, 30, 40, 90, 100. So 100, 200, 400, 500, up to 1000, 1000 to 10,000. So I'll have the frequencies log of omega plotted on the x-axis and magnitude on the y-axis. This magnitude is in decibel. So we saw in the last class what is decibel. 20 log to the base 10 of that factor is the decibel value of that magnitude, isn't it? So 20 log to the base 10 of k, whatever is the number. If that number is, let us say, 10. So log of 10 to the base 10 is 1. So 20 into 1, it is 20. So 20 decibel will be the value corresponding to constant k. That will be magnitude in decibel. So if that is 10, if that value of 20 log of 10 to the base 10, if it is 20, whatever it is, so if it is 20, so I'll be having on the y-axis decibel scale. I'll plot 10 decibel, 20 decibel, 30 decibel, 40 decibel, maybe multiples of 20, 20, 40, 60 on the y-axis. On the x-axis, I have frequencies, logarithmic scale of frequencies in 0.1, 1, 10, 100, 1000, 10,000, like that. I'll have the scaling on the x-axis. So for a constant term k, the magnitude plot is a straight line, right, which is above this omega scale. So positive side of the decibel scale. So if k is greater than 0, it is on the upper side, positive side of magnitude. If k is less than 0, it will be on the negative side. So, but it will be a straight line. So the magnitude plot for constant k in Bode plot is a straight line parallel to x-axis. Similarly, Bode plot for poles and zeros at the origin. If you just remember, pole at the origin or zero at the origin, S term in the denominator corresponds to pole at the origin, and S term in the numerator of the transfer function is called as zero at the origin. So what do you mean by zero and pole at the origin? Zero at the origin, if I put S is equal to 0 in that factor, the entire ratio becomes 0. In the pole of the at the origin, if I put S is equal to 0 for the denominator value, the entire ratio becomes infinity. So these are called as poles and zeros at the origin. Now what is the Bode factor magnitude plot? So for pole, Bode diagram of 1 upon j omega, that is 1 upon s, that is Bode diagram for a pole at origin. This is the magnitude plot and this is phase angle plot. So two plots we need to have in Bode plot. The magnitude versus frequency plot, that is the magnitude plot. Phase angle versus frequency plot, that is phase angle plot. So both these plots correspond to Bode plot, total Bode plot. Okay. For pole at the origin, 1 upon j omega, that is 1 upon s. How it is? It is a line of slope minus 20 decibel per decade. Now, if you refer any of the books on control systems engineering, we have got abundant copies of control engineering books of Indian authors available in the library. You can solve number of problems based on these Bode plots. It is very simple and straightforward procedure. You can follow. Remember, for pole at the origin, I have got a straight line of slope minus 20 decibel per decade. So how you have defined this slope? Minus 20 decibel per decade. Decibel, it is the magnitude. See, on the y-axis 0, 20, 40, steps of 20, isn't it? So, and y-axis, x-axis I have got 1 as the frequency. So this is 1 unit. So this is called as 1 decade. This is also called as 1 decade. This is also called as 1 decade. So okay. So this is 1 decade. And what is the value on the y-axis? It is 20. Right? So 20 decibel per decade. Now what is happening to the decibel value? It is decreasing from 20 decibel to 0 decibel. So what do you mean by this minus 20 slope? Minus 20 corresponds to negative slope. So what is negative slope? The value of decibel will be decreasing. So line of negative slope will be like this, and line of positive slope will be increasing value. If the slope is plus 20, there will be increment in decibel in magnitude per unit change in omega, isn't it? Per unit change in omega, per decade change in omega, per decade. So this is 1 decade. So 20 units per decade, it is decreasing. Hence the sign is minus 20 decibel per decade. So for pole at the origin, I have a straight line of slope minus 20. It is a straight line of negative slope. How much is the slope? 20 decibel. So minus 20 decibel per decade will be the slope. So if it is a single pole at origin, it will be having minus 20 decibel per decade. If I got a term called as a square, so second order, so 2 into 20, so the slope will be minus 40. If the term is s to the power 4, the slope will be 4 into minus 20, so it will be minus 80 decibel per decade. So in general, the slope will be power of s n into minus 20 decibel per decade. So this is the Bode plot for pole at the origin. Similarly, phase angle plot. How do we find out the phase angle? If you remember, last class we discussed phase angle phi for pole at the origin will be found out by taking tan inverse of ratio of imaginary part upon real part. Just refer back our last lecture. So tan inverse of imaginary part upon real part. Now imaginary part for s. So s corresponds to what it is? S is equal to j omega, isn't it? S is equal to j omega gives me frequency analysis. So if I write a complex number notation, the real part is 0, 0 plus j omega. So in 0 plus j omega, what is the real part? Real part is 0 and the imaginary part is omega. So if I take tan inverse, isn't it? Tan inverse, and it is in the denominator. So if I take a phase angle of 1 upon j omega, how much it will be? Phase angle tan inverse of, what is the complex number representation for 1? 1 plus j0. Imaginary part is 0, isn't it? So it is, phase angle will be tan inverse of 0, right? Minus, because the term is in the denominator, minus tan inverse of omega by 0. So tan inverse of infinity is minus 90, minus tan inverse of tan inverse of infinity, right? Tan inverse of infinity is minus 90. So the slope for pole at origin is minus 90. So for different values of omega, I'll be getting minus 90 only. So it will be a straight line at minus 90 degree for pole at the origin. Similarly, for 0 at the origin, what will be the magnitude plot? For 0 at the origin, that is S term in the numerator, friends. S term in the numerator. So magnitude of S term in the numerator provides me a slope of 20 log to the base 10 of S term, right? So it provides me a slope of plus 20 decibel per decade. So for 0 at the origin, I will have a straight line of slope, positive slope of 20 decibel per decade. So if it is a single 0, so s to the power 1, I'll be having a straight line of slope 20 decibel per 20 decibel. So this is 20 decibel per decade. This is 1 decade, right? Plus 20 decibel. So with increase of omega, decibel is increasing, that is positive slope. With increase of omega, decibel is decreasing, so it is negative slope. So for 0 at the origin, I have slope of plus 20 decibel per decade. So it will be a straight line of increasing slope. And if I got higher powers of S, if S to the power 2 in the numerator, so it will be 2 into 20 decibel per decade. So it will be plus 40 decibel per decade line. Okay. So what I do is, I draw a straight line of, in that case, it will be a straight line of slope plus 40 decibel per decade. Similarly, I can find out Bode diagram or phase angle plot for 0 at the origin. It will be a straight line. Once again, I take the phase angle of j omega, it will be a straight line of angle 90 degree, right? So this is the phase angle plot for 0 at the origin. Next factor is simple pole and simple 0. So what is the simple pole? If I got a factor of s plus 1 in the denominator, I call it a simple pole. If I got a factor of s plus 2 in the numerator, it is a simple 0. A factor in the numerator provides me 0, factor in the denominator provides me pole. So that this is what is meant. This is not j omega by z1. It is just j omega corresponds to 0 value, right? And this j omega corresponds to pole value. This is what is meant by this pi and zi. Z corresponds to 0, p corresponds to pole. Okay. So if I got a factor in the s plus 1 factor in the numerator, I'll be having simple 0 of the transfer function. If I got s plus 1 factor in the denominator, I got a simple pole of the transfer function. Okay, so once again, for a simple pole, I'll be having a straight line of slope minus 20 decibel per decade. Why minus 20? Because the magnitude value is decreasing. So this is a line of negative slope. So for pole, simple pole, I have got a slope of minus 20 decibel per decade. It will be a straight line of slope minus 20 decibel per decade. And for a simple 0, I have got a straight line of slope plus 20 decibel per decade. So these things you have to remember, friends. For simple 0 of a transfer function, I'll be having a magnitude plot as a straight line of slope plus 20 decibel per decade. So these could be the questions for your MCQ regarding Bode plot. Okay. Now, there's one more thing we have to remember, friends. For simple pole or simple 0, let us say simple 0. Where from I should start my simple 0 plot? At what frequency I should start my simple 0 plot? Now this frequency at which I am starting my simple 0 plot is called as corner frequency. Now this blue line corresponds to magnitude plot for simple pole. there is a line of slope minus 20 decibel per decade. But where from, at what frequency I am starting my magnitude plot for a simple pole. Now this frequency is called as my corner frequency. Now we'll see how to find out the corner frequency. We'll take a simple example. Suppose I have got a transfer function given as 1 upon 2s plus 100. Right? This is a transfer function corresponding to any electrical system, mechanical system, hydraulic system, pneumatic system, whatever is the physical formula system. I am converting it into a mathematical equation of operation, and I will be getting a transfer function in S domain like this. So what is the first step? Repose the equation in Bode plot form. What is this Bode plot form? I should convert this S plus 100 into 1 plus S form. So we call it as 1 plus tau S form. 1 plus tau S form, tau corresponds to time constant of the system. How to get 1 plus tau S form? By dividing this highest value in the numerator and denominator. If I divide the numerator and denominator by 100, numerator 1 by 100, denominator this entire term divided by 100. So what will happen? 2 divided by 100 makes it 50, S upon 50. The second term becomes 100 upon 100 is equal to 1. So this is my 1 plus tau S form. This tau corresponds to time constant, and this tau value is 1 by 50, isn't it, in this case? And the corner frequency is 1 upon tau, right? 1 upon tau. 1 upon tau is 50. So in other words, this transfer function is converted into, it was 1 upon 2s plus 100, now it is converted to 1 upon 100. K value is 1 upon 100, corresponds to steady state gain K. And denominator I have got 1 upon pi. This is my corner frequency into S. So 1 upon 50 is 1 upon pi, isn't it? So P1, this P1 is my corner first corner frequency. Second term is as it is. Okay, so from this transfer function, this K corresponds to 0.01. 0.01 corresponds to 1 upon 100. So this steady state gain K is 0.01. And what is the corner frequency of this simple pole? Corner frequency is 50. I was talking to you regarding corner frequency. At what frequency my Bode plot, Bode magnitude plot for simple pole starts is the corner frequency. At what value of frequency my Bode magnitude plot for simple zero starts is the corner frequency of that simple zero. So this is what is meant by this corner frequency, right? So whatever is this value is my corner frequency. So 50 is the corner frequency. So how should I plot? How many factors I have got? I have got only 2 factors. First factor is steady state gain, constant K factor, and second is simple pole. So I have got K is equal to 0.01 corresponding to numerator, and P1 is the first corner frequency for simple pole is 50. Just comparing this equation with this, I got 50. Or in other words, if I call this as 1 plus tau S, tau is equal to 1 by 50, and my corner frequency is 1 upon tau. That is 50 only. So this is the first corner frequency. The plot for constant K, just now we have seen how to have a plot for constant K. Is a straight line corresponding to, what is the value of K? K is 0.01, right? So 20 log to the base 10 of 0.01. So 0.01, what is the log of this log to the base 10? So minus 2.000, isn't it? Just by observation, we already studied logarithms. So minus 2 into 20 gives me minus 40. So on my graph paper, minus 40. This is the plus side, this is the minus side. Minus 20, minus 40. Minus 40, I draw a straight line. This is the Bode magnitude plot for this constant K term of 0.01. It is 20 log to the base 10 of 0.01. It is 40, minus 40. And for the simple pole, they call it as critical frequency. We call it as corner frequency. At corner frequency, so where from I should start my straight line of slope for simple pole. The slope is minus 20 decibel per decade. So this will be a straight line of slope minus 20 decibel per decade, right? And starting at corner frequency of 50 on my semi-log paper. So corner frequency of 50. So 10, 20, 30, 40, 50. At this corner frequency of 50, I'll be starting my line of minus 20 decibel per decade. So that will be the Bode magnitude plot for simple pole. Likewise, depending on number of factors involved in my problem, I have to draw the Bode magnitude plot and Bode phase angle plot. Okay, we'll move further. So these are the lines I need to draw. At corner frequencies, I need to draw the lines of those slopes. Let us take a bit complicated example. Quickly, we'll do this. If I got a transfer function s g of s initially is equal to 50,000 into s plus 10 upon s plus 1 into s plus 500. This is the transfer function in s domain that will be obtaining. So first step is put s is equal to j omega. If I am doing frequency response analysis and I need to draw, the question asks is obtain Bode magnitude plot and Bode phase angle plot. So substitute s is equal to j omega, so it becomes g of j omega is equal to 50,000 into, instead of s, it will be j omega plus 10 divided by j omega plus 1 into j omega plus 500. What is the first step? Always get the poles and zeros in a form such that the constants are associated with j omega terms. So it is called as 1 plus tau s form, right? So here j omega plus 10, I want to convert it into 1 plus tau s form. So dividing it by 10 makes it 1 plus j omega by 10. It is 1 plus tau s form. This is already in 1 plus tau s form. This is not in 1 plus tau s form. So divided by 500 makes it 1 plus j omega 500. So it is 1 plus tau s form. So in the above example, we do this by factoring out 10 in the numerator, dividing it by 10, and 500 in the denominator. Okay. So numerator divided by 10 and the denominator divided by 500, right? And taking out that 500 common, taking out that divided by 10 common, right? So what happens? So we are taking out 10 common, isn't it? So 10 common if I take, multiplied by 10, right? So it will be j omega divided by 10 plus 1. So it is 1 plus tau s form, right? So it becomes, and denominator, here nothing to be taken out common. Here 500 is to be taken out common. So 500 I have taken common into j omega plus 1 into j omega by 500 plus 1. So all these are converted into 1 plus tau s form, 1 plus tau s form, 1 plus tau s form. So in the process, what has happened? We have got these multiples. So I have to just simplify this, removing these two terms. What happens is only 100 remains in the numerator, and I have got 1 plus tau s form in the numerator, 1 plus tau s form in the denominator. And 1 upon tau are the corner frequencies. So this is 10 is the corner frequency for simple 0, 1 is the corner frequency for simple pole, 500 is the corner frequency for simple pole, second simple pole, right? So, and we don't have poles or zeros at 0 because we don't have any s term as such, isn't it? S term in the numerator, no s term in the numerator, no s term in the denominator. So no poles or zeros at the origin. So whatever 0 I have got, it's a simple pole or first order pole at s is equal to minus 10. 1 0 at s is equal to minus 10, 1 pole at s is equal to minus 1, and second pole, simple pole at s is equal to minus 500. So 2 poles and 1 zeros and 1 constant term. So first thing, get a magnitude plot for k term, constant k term. Now what is the constant k? It is 100. So 20 log to the base 10 of k. So that is 20 log to the base 10 of 100. So 100 is, what is log of 100 to the base 10? 2. So it is plus 40 decibel line in this case. So that will be in the magnitude plot, it will be a straight line parallel to x-axis, parallel to omega axis at value plus 40 decibel. So that will be a straight line. Now I have got, as I said, simple 0 at corner frequency of 10. Simple 0 at corner frequency of 1. Simple pole at corner frequency of 1. Simple pole at corner frequency of 5. Now, where from I have to start now? See, I have to draw a straight line of slope either plus 20 decibel per decade or minus 20 decibel per decade. At what frequency I should start? It is very simple. Out of zeros and poles, start with the lowest value, right? So lowest value of corner frequency is 1. And thereafter I got the corner frequency of 10. Thereafter I got corner frequency of 500. Let it be any pole or any zero. Start with the lowest value of corner frequency. In this case, it is 1. So I'll be having slope changes at corner frequencies 1, 10, and 500 in the increasing order. So on my graph paper, I'll be just marking corner frequency at corner frequency of 1. So omega C1, the corner frequency 1 is 1. So at 1, I'll be having first corner frequency. At omega C2, second corner frequency is at 10 log of omega on x-axis. Second corner frequency, and third corner frequency is at 500. So I have to mark on my graph paper. Okay. So that is what is written. And observe the order in which the poles and zeros occur. This is the secret of being able to quickly sketch the Bode plot. In this example, we first have a pole occurring at 1, increasing order, which causes a Bode to break at 1 with a slope of, for pole, I'll be having a slope of minus 20 decibel per decade. And for zero, simple zero, I'll be having a straight line of slope plus 20 decibel per decade. So the Bode plot, magnitude plot breaks at first corner frequency with a slope of minus 20 decibel per decade. Right? Minus at first corner frequency is 1. Second corner frequency is 10. Remember? First corner frequency is 1. Second corner frequency is 10, and third corner frequency is 500. So on my graph paper, x-axis I have got log of omega, 0.11. This is 1 decade, second decade, third decade, fourth decade, fifth decade, 5 cycles, right? So I first of all mark the corner frequencies. First corner frequency is at omega is equal to 1. Second corner frequency is omega is equal to 10. And third corner frequency is omega is equal to 500. 1, 2, 3, 4, 5. 500. So this is my third corner frequency. I mark the points. Then my line starts with the constant term k. What we had written? Constant term k. The straight line parallel to x-axis is 40 decibel per decade. Up to what point? Up to first corner frequency. So 40 decibel line, straight line for k term, it is up to first corner frequency. And thereafter, I have got a simple pole. So simple pole starting at first corner frequency and ending at second corner frequency. Second corner frequency is 10. And what is the slope? The slope for simple pole is minus 20 decibel per decade. So see the term, right? Minus 20 decibel per decade. So that is from first corner frequency to second corner frequency. And thereafter, what I got the second corner frequency, it is for the zero. For a simple zero, what is the slope of the straight line? It is plus 20 decibel per decade. So already I am with minus 20 decibel per decade slope plus 20 decibel per decade. So what will be the slope of the line? Minus 20 plus 20 it will be a line with zero slope. And that's why for zero, simple zero, I'll be having a straight line of zero slope. That is a line parallel to x-axis. Are you getting this point? This is a straight line with minus 20 decibel per decade slope, right? And then for a simple pole, then for simple zero, I've got a straight line with slope of plus 20 decibel per decade. So minus 20 decibel plus 20 decibel. So the slope becomes zero slope. So that's why it is a straight line starting from second corner frequency of 10 value up to the next corner frequency, that is 500. So it will be a straight line of net slope of 0 decibel per decade up to 50 omega, 50 radian per second corner frequency, second corner frequency. And thereafter I have got second pole, right? From second corner frequency, I have got the third factor, that is simple pole. And it will be having, simple pole will be having a slope of minus 20 decibel per decade, minus 20 decibel per decade, starting from the second corner frequency and going up to infinity. So this is my magnitude plot for this transfer function. Similarly, I can have a phase angle plot. A phase angle plot for each of the frequencies. What I have to do? I have to get the phase angle. The phase angle for this zero. How to find out the phase angle at zero? Phase angle at the numerator term. So it will be phase angle of this numerator term will be tan inverse of imaginary part upon real part. Now what is the imaginary part? Omega by 10 is the imaginary part. What is the real part? 1. So omega by 10, tan inverse of omega by 10 will be the phase angle for 0. Please be attentive. So tan inverse of omega by 10, tan inverse of omega by 10. So I put omega is equal to 0.1. whatever value of tan inverse of 0.1 by 10 I get, the tan inverse value, that will be my phase angle in degrees. So I'll be plotting corresponding to 0.1. I'll be having one more paper or below this semi-log paper magnitude plot. I'll be having degree demarcations here, 0 degree, plus 30, plus 60, plus 90, plus 120, and beneath 0 line I'll be having minus 30, minus 60, minus 90, like that, those plots for phase angle. So for the first factor, maybe I have a phase angle of corresponding to frequency of 0.1, the phase angle, whatever value I'll be getting that. For second factor, similarly, I'll be having tan inverse of omega by 1. For third factor, tan inverse of omega by 500 will be, and the net of this numerator term minus denominator term, addition of these angles gives me the net angle. So for different values of frequencies, for 0.1 frequency, I get the resultant angle. So I plot phase angle of minus 90 corresponding to omega is equal to 0.1, corresponding to omega is equal to 1. What will be the net angle or the resultant angle for all the factors? I'll be plotting here. For omega is equal to 10, omega 100, omega, I take 5, 6 points and I mark the phase angles in degrees and I plot the curve. That will be the phase angle versus frequency plot. Friends, okay. This is what is described here. I'll be having the phase angle plot. We can make use of MATLAB program also. It is very, very simple, friends. When you come to college, you will learn how to use this MATLAB commands. MATLAB has got a control system toolbox wherein I can plot any frequency response plot by using MATLAB. It's very simple. This is the given transfer function. I have to simplify this transfer function 5000s plus 5000 to 10, so 50,000 divided by, I just multiply these terms, I get quadratic term, that is s square plus 501 s plus 500. So I have to just simplify and write the transfer function. MATLAB program is also very simple. Numerator NUM is equal to, the parenthesis corresponds to the matrix, row matrix. So these are the multiples of s and the constant term. So 5,000 and 50,000 I write denominator, multiples of s term. S square term is 1, s term is 501, and the constant term is 500. So 1, 501 and 500 in the denominator. And I simply use the command Bode into bracket numerator and denominator, num and den, bracket complete. So just execute this command, I'll get both the magnitude plot and the phase angle plot. The following are resulting magnitude and phase plot. So this is the magnitude plot, magnitude in decibel versus omega logarithmic frequency. This is the phase, this is the magnitude plot I'll be getting directly. You can see two types of plots here. These are the approximate plots, right? The way we drawn in the earlier example, isn't it? These are the corner frequencies. First corner frequency is 1, second corner frequency is 10, and third corner frequency is 500. So this is red line is the approximate Bode magnitude plot, and these are the asymptotic plot. These are called the exact plots. Right? There are some error corrections. Those are corrections. Those are to be made. We are not getting into details. But if I execute my MATLAB program, I'll be getting both approximate plots, magnitude plot, and exact magnitude plot. Similarly, phase angle plot. As I was telling, x-axis is once again omega, y-axis is phase angle in degrees. So for different values of frequencies, 0.1, 1, 0.1, 1. 10 to the power 0 is 1, 10 to the power 1 is 10, 0.1, 1, 10, 100, 1000, 10,000. So I'll be having the phase angle plot for these factors. So by using MATLAB, I can have a magnitude plot and I can have phase angle plot. And by using the earlier procedure I described earlier, we can always plot it manually also. It is very simple procedure. We need to, as I told you, come to library. We got wonderful Indian author books. Refer to the chapter on any of the control engineering books. You can refer number of maybe 70, 80 books, copies of Indian author control system books are available. Refer those books. Even wonderful videos are available on YouTube. You can refer those videos. The procedure is very simple. It is a matter of patient listening and observing. Follow these videos and practice these plots for variety of factors, right? And learn how to plot the magnitude plot and phase angle plot. Now, one more important thing. I talked to you about the stability of a control system, friends, isn't it? Stability is just from pole zero plot, the system, if the roots lie on the left half of S-plane, the system is stable. If the roots lie on the right half of S-plane, we call it as, I'm talking about pole zero plot. If the roots lie on the right half of S-plane or right half of imaginary axis, the system is unstable. And if the roots lie on the imaginary axis, the system is marginally stable or conditionally stable. Similarly, from the Bode plots, we can have stability comments here. Now see, this is just one example I'll try to explain. This is the magnitude plot. This is the zero magnitude line. Now wherever this Bode plot, magnitude plot is crossing the 0 decibel line is called as the gain crossover frequency. The frequency at which the gain is crossing the 0 value. Listen to me very carefully. The frequency at which the gain is crossing the 0 decibel mark. At this point, maybe here I have got maybe 4,000 radian per second. At 4,000 radian per second, the gain is crossing 0 decibel value. This is called as the gain crossover frequency. The gain crossover frequency, it is designated as G suffix C radian per second. So that is called as gain crossover frequency. The gain crosses 0 decibel line. So gain crossover frequency. If I just extend this gain of crossover frequency point on phase angle plot, just dotted line if I draw here, at that frequency of, let us say, 5,000 frequency, whatever is the phase angle from 0 angle, this is called as the phase margin at gain crossover frequency. So phase margin we obtain at gain crossover frequency. So this is the phase margin. Similarly, wherever my phase angle crosses my 0 degree line, it is just beyond this paper, right? Wherever it crosses the 0 degree line, it is called as phase crossover frequency. The frequency at which the phase angle plot crosses the 0 degree angle is called as phase crossover frequency. Phase crossover frequency. So it is omega suffix p radian per second is phase crossover frequency. Now suppose that phase crossover frequency is somewhere here. If I just extend this line on my magnitude plot, so wherever it intercepts my magnitude plot, and that magnitude from 0 is called as gain margin. So at phase crossover frequency, I get gain margin. Listen to me very carefully. At phase crossover frequency, I get gain margin. At gain crossover frequency, I get phase margin. I repeat, at gain crossover frequency, the frequency at which gain crosses 0 decibel value is called as gain crossover frequency. At gain crossover frequency, I get phase margin. At phase crossover frequency, I get gain margin. Now, regarding stability, there is a general comment for stable system. The gain margin and phase margin should be positive for stable system. If either the gain margin is negative, either the phase margin is negative, the systems are said to be unstable. This is what is the prediction from phase from Bode plots. So if we solve number of problems, we will be getting different cases of unstable system, different cases of stable systems. We can even find out the margins within which the system is stable, the system becomes unstable. All these formats are possible. For this, friends, we need to solve more number of problems on Bode plots. It's a very simple, straightforward procedure. As I told you, you either refer the net, refer the YouTube videos, refer the books. We have got wonderful books in the library by Indian authors. We can solve number of problems on Bode plots and learn to comment on the conditions for stability of these Bode plots. So thank you for watching. Thank you.